something which is clearly related to quantum filtering, and we'll see that it can be used also for dynamical parameter estimation. It's not new things, but it's things that we have learned by collaboration with Serge Adroche group in Paris, and on an experiment of measurement-based feedback and stabilization of photons. So what is so maybe you know already this picture. So this is, I will call this setup, it is the LKB photon box for Laboratoire Kessler-Brussels. Okay? So the goal of this experiment was in fact to stabilize photon number state, okay? Which are in fact in this quantized mode between two very high finesse cavity. And for this, what we have probe atoms in a Rydberg state, which is this pink torus. They pass through the cavity, clearly, and here they are detected, and here you have the feedback loop, but it is a measurement feedback loop. All this part is a quantum evolution. Here it is a quantum measurement, but all this part is classical. Okay, here you have a classical signal, which is the detector outcomes. Here you have a real-time computer, and here you have your control, and your control is a coherent pulse. So for this system, the sampling time, so the time between two atoms, is 80 microseconds. So in 80 microseconds, we have time to do, in fact, in real-time computation with a computer. Okay, so it's maybe there is a small animation that has been done by Igor, so you will, if it works, I think. Oh, yes. So what you have here the atoms, okay? They are prepared in a Rydberg state, okay? And they can be considered as two-level system. So they are flying atoms. Here, they get outside the box in the ground state. Here you have a first manipulation of the atom only with a pi/2 pulse, okay? So now it is the atoms outside this first cavity is a coherent superposition of the ground state and the excited state. Here you have now the interaction between the atoms and the probe atoms and the photons. It is a dispersive interaction, so no exchange of energy, sort of exchange of phase, okay? Here you have, after that, you have a post-manipulation of the atoms. It's another pi/2 pulse. And here in this detector, it is a ionization detector, you detect either if the atom is in ground state or in, okay, in excited state. So this is essentially the quantum part of the evolution, okay? And now you enter into the classical part. Okay, so here you have detector outcomes, either -1 or +1, say, okay? And here you have a computer, so you use this information, you do some computation, and after that, you send some order to this actuator, which is in fact an antenna, and you decide to send, during a certain short time, a pulse, coherent displacement pulse of amplitude A and phase phi, okay? So, and all this loop is 80 microseconds. And then you continue. Okay, all this time. Yes?
The pulse that you apply,
yes.
Does it have the same interaction as the one inside the cavity?
No, it's just the pulse that you applied, it's just with an antenna, okay? And you send, in fact, a certain number of, I will say, classical photons, coherent displacement. So the pulse here, it's just a coherent displacement of the wave function of the photons.
Oh, right.
Only this. And just you, in fact, control the amplitude and the phase of this pulse. Okay, just this. Yeah. So it is clear that it is in the ideal situation. Okay, so you have here, what you have is the atomic preparation is not perfect. Sometimes you have no atom into the slot of 80 microseconds. Sometimes you have one atom. Okay, so it is given by the pulse occupancy. Sometimes you have two atoms, it happens. Okay, here in the cavity here, you may have finite photon lifetime, clearly, so you have some decoherence due to the non-perfect mirrors. And here, clearly, in the detector, what you may have is a certain number of detection that you lose, the detection efficiency, and you have also fault detection. So the atom collapses in E or in G, but the detector says you that it is the reverse way. Okay, so okay, and an additional point is that you have a delay. Okay, so you have a delay between the detector and the cavity. Okay, so I will show you now some experimental results, okay, that have been published 3 years ago. And for this, you have a detection efficiency of 40%, error rate 10%, and you have a sampling, a delay, which is the delay of feedback loop, it of four atoms, okay? 4 steps delay. So it's not a small delay, okay, for this system. And to do this, here you will see, I will show you some real information, real data. So the first plot, here it is the time, okay? So the first plot is the detection. So you see when you are in red, you detect in the excited state either 0 atom, 1 atom, or 2 atoms. In blue, you detect the same thing for the ground state. Here it is the Lyapunov function, but I don't speak of the feedback scheme. Here I will speak on the estimation scheme. Here it is the coherent pulse. So the coherent pulse is always real. Since you are considering only photon number state, you have no phase. So you can fix the phase to be real, and all the things, all the computation are with real density matrices. So here, this is the control. The goal was to stabilize free photon in this experiment. And here, it is the population. So in green, you have exactly the population of free photons. In red, you have the population below 3 photons, so it is population of 0, plus 1, plus 2 photons. And in blue, you have a population above 3 photons. It's 5 until 8. And we truncated the Fock space to 8 photons. Okay? And here you have snapshots of a density matrix, which is real. So here you see that clearly, since so in open loop, when you plug the control to 0, it is Q&A measurements of photons. So it is, if you want to reach 3 photons, just use a good initial state. And the good initial state is to use, it is a very standard preparation, a coherent state with 3 photons. And here you see the density matrix of a coherent state with 3 photons. And the goal is, in fact, to stabilize this system, in fact, where the density matrix is concentrated on the diagonal at this position, corresponding exactly to 3 photons. And here you have snapshots. And the difficulty of the feedback loops, it is because once Q&A measurements, it just concentrates very rapidly the density matrix on the diagonal, okay? And then after that, you have the cavity decoherence that in fact push you, but in the slow time scale to 0, in fact. And we want to fight against this decoherence, not to take advantage of the Q&A measurement to be on the diagonal, and then to avoid the decrease to 0, the slow decrease to 0. But with this, when here, it is a coherent pulse. A coherent pulse, when you push a coherent pulse on a photon number state, you inject off-diagonal elements. And the trick was in how to manage this pulse. So you see that here, you see that we have almost reached, in fact, the good photon number here, because we are in green. And here something happens, which means that the cavity destroyed 1 photon. So you have something red appearing. And then you have to decide on what is the sign of the pulse. So you shake the things such that after a certain time you recover things and so on. I will not speak on the feedback loop. I will just speak on the estimation here. Okay, we concentrate on these things. So maybe first some.
Sorry, how fast is a coherent pulse? How fast is it to switch it on and off? Is it
On and off, I think it was a few tenths of microseconds. So you have a feedback loop. The feedback loop is 80 microseconds.
Right.
Okay, so the traveling time of the atoms is more or less one half of this time. Then you have some time for the computer, and for the coherent pulse, it is 10 microseconds maximum. So they have an amplitude, and they just control the time. Okay. So now you will see. So it's real data. So I will explain how we compute this, in fact, in real time. Okay, just this. So here this is, so it's two slot by two slots. So you see first the things, and you see that the coherent pulse gives off diagonal elements. Okay. So you see, so you fight against the decoherence of the cavity. Okay. Just this. So I will focus on this part, computation of these things, not on the computation of a control law. Okay. And the control law, it is a static function of these things. So we use, it is a nonlinear static function of the density matrix. So it's a full quantum state. We are in a non-commutative regime. We are not concentrated on the diagonal. Okay. So if you consider the simplest model in the ideal case of this system, so from an, I will say, mathematical system point of view, what you have is a Markov chain with input u. U, it is this number, which is the amplitude of a coherent displacement. It is u. You have an hidden state, ρ, which is the density matrix, and you have the measure output, which is y, corresponding to the atoms. Okay? So what you have is this Markov chain. I will detail a little bit how the construction of this, but it is something which is in a set very standard. Here you have the measurement operator, mg and me, okay, which are in fact cosine and sine of a phase, and the phase is just a function of the photon number operator. Okay, so you see that mg squared plus me squared is equal to 1. Okay, it's obvious here. So this is the Q&A way to measure photon without destroying them. And then the control after that, so you measure first the photon with the collapse, and then you control your density operator by a current displacement. So it is nothing but this unitary operator where A is the photon number, photoannihilation operator. And the goal is very basic things. When you put U is equal to 0, you know that any photon number state is a fixed point of this. Either you collapse in G or in E, it doesn't change ρ, if ρ is a photon number state. So what you want to do is you have a fixed point, and what you do is what you want to stabilize this, okay, by U. Okay, and what in open loop this system is a certain sense stable. Okay. So it's just okay. So what is the structure? So the structure of a feedback loop, it is this one. In the ideal case, it is, so at least the estimation procedure is obvious. You use an initial estimate of ρ at time 0, which is the coherent state with free photon. Since you know exactly what are, in fact, the jump due to the atoms, and you measure them, you inject them here, and you know exactly what you have used as coherent pulse, here you have just estimate. Just, in fact, show you the path of your, in fact, quantum trajectory. You do not need to use some random numbers. They are given by the detector. And then, so here the stabilizing feedback is a function which is like this, with a couple of things. I will not detail this part. I will detail this part when you have measurement imperfection and decoherence. Okay? So, in a realistic case, I will show you how we simulate the closed loop system. Okay? And so what we use is here for the experiment, we use as a state, even if you have, in fact, imperfection and decoherence, we still use psi, a pure state. Okay? And then we corrupt this state and the information that gets outside, in fact, the experiment here, okay, by some, in fact, classical, in fact, stochastic process. Here we estimate the density matrix, which is not related to it because it is a mixed state, and then we compute U. So I will show you these two programs, I think. It's maybe the best way to understand what is going on. So here it is the model of a cavity. So maybe it's the best way to see this. The model is a cavity, so phi, okay, pH, it is the wave function. So here you have a measurement operator, okay, and here it is the normalized state if you measure G or E, okay? Then what you do is first you simulate the fact that your atom sample is not perfect by your first random number. Then you simulate the detector efficiency. But the detector efficiency, the atom is detected, and then you simulate with another random number the fact that you collapse in G or in E, okay? And then we simulate, okay, with another random number the fact that you may have wrong detection. So we mixed, in a certain sense, quantum probability with classical probability, like this, okay? And we do exactly the same thing, okay, for all this trick. So, and for cavity decoherence, it is exactly the same thing. Okay, with minus one photon, plus one photon, and no jump. Okay, and the coherent displacement is this. So here in this model, so we use a wave function which is pure. Okay. But in the quantum filter, what we have to do, we use mixing because we have not all the information. So we use partial mixing, okay? Only this. So when you see it is rho G and rho E, it is this kind of things. And here you recognize here it is a Krauss map. Here it is the probability that you compute with your estimate. And then you take into account that you have a certain imperfection in the detection process. Okay. And then you take also into account the decoherence. So, and with this, you can simulate what is going on this is a simulation, so it is a snapshot, exactly the same thing. So you see, so in the real life, what you have only access to the detector. Here I have simulated only 0 or 1 atoms. And here it is the feedback. And here it is your estimate. But here it is interesting to see what is this, I will say, wave function inside the box we use to simulate. So, and you see that you have a relation, but it is not exactly this. Okay? This is here, it is the photon number 3, population 3, population less than 3, and population above 3. Okay? And here it is for the wave function, and here it is for our estimate, which is, for physicists, it is the quantum state, this one. Because this one is, you can use it in simulation, but it is impossible to get it in the real thing. So here, these things summarize the information you have on the system. But for simulation, this state could be interesting because you use only a wave function instead of a density matrix, so it could be interesting. Okay? But with these things, you represent completely the statistic, the input-output statistic of your system. You can either represent it by this or by this state, which gives you exactly the same statistic. But one state is, in a certain sense, observable. You can manipulate it and you can see where it is. The other state is not observable. You cannot use it. You cannot estimate it. Yes?
So does it mean that the estimation fidelity is only about 90% in this case?
No, this is the true quantum state here. This is something that is, in a certain sense, a mathematical construction for a physicist that you can use in simulation. It's something which is difficult to understand. But so when I discuss with Jean-Michel Raymond or Michel Roller-Serge Haroche, this is the true quantum state. This is a simulation trick for them.
Yeah, but in terms of fidelity, the state you estimate compared to the true state, does this figure indicate
the true state is this one for them. Sorry about this. So, yes.
Maybe I could rephrase that.
Yes.
It's interesting, say, they're in there in that trace that the estimator thinks that something has happened to the photon number, but the simulation is going on. So somehow or other, because, I mean, it is true that the noise in your system is limiting the average fidelity with which you're preparing Fox state 3. And somehow or other, the jumping around in this trace is telling you about that somehow. Is that fair enough?
Yes.
I'm trying to avoid a language whereby the top plot.
Yes, the top plot.
True
Yes,
state.
exactly. So
You could ask about the average fidelity with the Fox state over many experiments.
which means that from a statistical point of view, what is this guy? This guy is the estimate of the orthogonal projection of this guide, knowing the initial condition and the past detector outcomes.
Are you trying to distinguish between conditional and unconditional states?
So this is the conditional state,
That's the conditional one.
based on all what you know.
The top one is unconditional, is it?
No, the top is just to represent the input-output statistic.
Yeah.
I can
the top one
do
involves a simulation
exactly the
that
same
knows
simulation.
Exactly when photons leave and into the cavity.
Just this.
So the
It knows the
is
top one is a pure state for an imaginary observer who's monitoring everything that's going wrong.
So, and maybe we'll continue here because it should, maybe it could be more simple to use what is behind the equation. So what we have learned by working with this group of physicists is that for this, what we combine is only Bayes' law, conditional probability, Schrödinger equation clearly for the unitary propagation, the partial collapse of the wave packet, okay, where you have an observable degenerate spectrum, and clearly the fact that on your composite system, the system plus the matter, you only measure the matter. So which means that the observable is highly degenerate, in fact, observable. Okay, just this. So this is, I think here it is something that you know already. I will not emphasize on this. I will go quite rapidly through this. So the system is a composite system, okay? So I consider the quantum evolution part. So your wave function is here, your matter is here. So harmonic oscillator, two-level atoms, so a spin-spring system. And if you look at the quantum evolution, it is this. When the atoms get outside the box, it is in a separate state with a photon, wave function of a photon, wave function of the atoms. Just before the detection, it has undergo a unitary evolution, but I will not explain precisely, with these two measurement operators. And you have a partition of unity here, usual things, classic standard measurement theory. Okay. And now, just before the detection, you have a partial collapse of the wave packet, what gives you this, okay? Standard things. And the information get outside the system through the fact that the probability of detecting either E or G depends on rho. It's the way the information gets outside the system. Okay, and here what you have is if you have no information, you have still the modification of rho, knowing that you take the conditional expectation of rho after the jump based on the knowledge of rho before the jump, and if you have no detection, if you do not have any detection, okay, then it will change the state. So this is the back action of the measurements on the state. Say, and you recover a cross map and quantum channel and all these things. Okay. Now, assume just that the detector, you have error rates. Just consider this. So error rates, they can be represented by classical probability, which means here it is, you assume that the detector has, the atoms have really collapsed in G, but the detector tells you that it is E. So you have an error rate, which is called eta G, which is between 0 and 1. You have exactly the same error rate when the atoms collapse in E, but the detector tells you the opposite. Okay, so you have two numbers, and these two numbers correspond in this experiment to the contrast of the rim fringes, in fact, in this field. So, and these two numbers, now, what you have is, since all what you can do, since you know that you have some detector error rates, what you can do is just to compute the expectation value of rho plus, knowing the wave function, okay, just before the system. And if you combine this plus the probability, in fact, to have a collapse in G or in E, you use classical Bayes law, what you have is something like this. And it is very, very interesting to notice that here you have a mixing, clearly, of what is going on. And assume that your detector tells you G. Okay, so you have a mixing of, effectively, you have a collapse in G here, but you have also part of your system is in E. Okay, so you take this combination, and then you take the trace to normalize. And what is very important is that the trace here, it is exactly the probability that your detector detects G. Okay? This is something trivial, but it's very important. Okay? So, in a certain sense, rho plus is no more pure, if rho is pure, clearly. And so it is a mixed state, but C plus has no meaning from an experimental point of view. But from a numerical point of view, you can still use it by, in fact, simulating this error rates with classical probability, with random numbers. Okay, just this. It's exactly what we have done. So if you add to this photon decoherence. Photon decoherence is when you have no measure. And in this case, you just have a cross map. So you combine all these things, and what you have is this. For the photon box, when you combine all these things, what you have is the estimate at state k plus 1 is equal to the estimate at state k plus a mixture of different cross operators. This cross operator, you have a bunch of cross operators, you have 21 cross operators. Okay, so if you take the sum over all the mu's of mu rho, mu dag, okay, you have a cross map. Okay, but you partition this cross map through a left stochastic matrix. It's the way you, in fact, you store your classical probability. So you mix classical probability, quantum probability. And then you take some partial average, okay, of this cross map. And then you normalize. And the normalization is exactly the probability that your detector detects mu prime. Okay? So for the photon box that we have only 6 detection possibilities. So either you detect nothing, which means that you have no atoms, but you may have 1 atom or 2 atoms of few probability. You have to take this into account. You detect GE or double G, or GE or EG is the same thing, or EE. Okay. And here you have this density matrix. It is based on classical error rate and so on, and you can compute it. Okay, this is the stochastic matrix. And you see that the sum of these columns are 1 always. Okay. So it is exactly what we have used for this experiment. Okay. Now, the general things behind this is, and I think it is typically related to the optimal and Belafking results, but it is in discrete time here. So you assume that you have a Markov process, which is always pure, when you detect all the jump in your system, okay? All the things. You have a complete knowledge of what is going on inside your system. Your state remains pure. And then you corrupt all this possibility by this left stochastic matrix. And in this case, what you only have as a quantum state, it is the expectation value of a propagator of these things, of a projector of these things, knowing the initial state and the past detection outcomes. And if you want to compute this is the optimal estimation of your quantum state, you use this thing, okay? Partial mixing, in fact. Not full mixing with a Krausmath, but you use partial mixing, just this. And the normalization gives you information on rho k, because the probability to detect mu prime k at step k is given by this. So the main trick is this. And now what we have is, maybe for physicists, they know that this kind of filtering process is a good process, which means it tends to forget its initial condition. But assume that, which is much more mathematical issue than a real physical issue, but I think it is an interesting problem. It is the stability of this filtering process. So your quantum state corresponds to, in fact, this expectation value, and so this recurrence, okay, with a perfect initialization. If you have some error, typically an initial condition error, so what you will have exactly the same mu detector outcomes, but you will use a different initialization. Does this quantity converge to this quantity? Which means that you have a filter. A filter is something that forgets its initial condition. It is stable. And the problem of stability of quantum filtering is not so simple as far as I discovered here. Okay? So what you have is this. If you want to set up this in a more abstract manner, you have clearly a Markov chain with two states. Okay, so you have these outcomes are probability things, and these are this probability, and the probability depends only on rho k, not on this guy. Okay, but you use exactly the same thing here. Okay, to iterate. So this is a Markov chain with a certain probability law, and the issue is, does the blue one converge to the real one here? So you have in continuous time a partial resonance of Hammond 100. He has looked at this problem, but this. And what we have discovered is that the system is stable, not convergent, which means that you can prove that whatever these things are, the fidelity between rho and its estimate is something that tends to increase in average, which means that its expectation value at the next step, knowing rho k and rho k minus 1, is greater than this one. Okay, you know that it is increasing. So it tends to converge, so in average. Okay, this is, and this thing is based on a matrix inequality, which is something like this, that I have proved in 3 years ago. And it is something which is not very complicated, and maybe it is related to what in fact, Michael has said about Cauchy-Schwarz fields and quantum channel, because try to understand why it is like this. And it, okay.
But the fidelity might not go to 1.
Yes,
Are there any conditions under which it actually...
don't know. So the problem, the mathematical problem is this one. So you give this operator and this left stochastic matrix, and can you prove that you have asymptotic convergence of rho to rho k in an almost sure way? And to have checkable condition on this. As far as I know, it's an open problem, these things. So for Bayesian parameter estimation, the trick is very, very simple. So it is just to consider, in fact, assume that you have only 2 parameters, and you want to see if your system is in parameter A or B. So in fact, what you will use 2 blocks of density matrix, rho A and rho B, and iterate, but normalize by the sum. And in this case, it is exactly the same thing, okay? But just add with a pure Cartesian product your parameters. So it is something which is well known, in fact. So you have a nice paper where, in fact, in the last CDC, where they can recognize difference, in fact, topology of different circuits. Okay? You have 2 topology, A and B. You have measurement. You want to see if you are in topology A or topology B. Something like this. And it is related to, this issue is related to an old paper of, I think, at Mabuchi. And you have also all these things are well explained in paper of Weissman and also of Klaus Moll more recently. But it is more in fact, in the continuous time things, but it is the same thing. Okay. So it seems what we have learned is this, on these experiments, but to do for this discrete time system quantum filtering, what we have is just to combine these 4 points, just this. And then it is clear that this is easy to use. Computing a unitary propagator could be not so easy, clearly. We may have some difficulties here to have some formula. Here it is more or less okay and here okay. So the technicalities in the computation is in the integration of a Schrödinger equation to get the propagator. And with this, what we can see is that it seems to me that any Markov discrete time models of open quantum system will have this structure. Okay. When you take the input-output system. So your classical input will influence this operator, and mu, and the measurement will be given by mu prime here. And using this, you can modelize, it seems to be most of open quantum system, if you assume a Markov assumption, clearly. And associated to this, what you have is the cross map here, and the imperfections are coded in this stochastic matrix, just this. And you combine this. Okay, and in general, what you have this stochastic matrix is a rectangular matrix, so with a large number of columns, okay, and few lines corresponding to the detection. And if you have only one line, so you have no information, and this formula gives you that eta is equal to a line of 1, and then you recover the Krauss map. Okay? So you have a continuity between all these things. Quantum channel and the fact that you can inject also the knowledge, in fact, of your measurement, just by this. Okay. And now, I will propose this, not new, but it is just a shortcut to see that, in fact, continuous time systems are almost of the same structure. Okay, so I will take just the example of diffusive systems. So here, it is this equation with a Limblad-Kosakowski evolution, okay, Hamiltonian part and dissipative part here. And here you recognize with detection efficiency, okay, the Wiener process. And the Wiener process is related to your outcome. It plays the role of mu prime this, by this detection efficiency, eta. Okay. So, and it is clear that when you take the average, you recover to this, and I will show you that this dynamical equation can be written like this, and this equation can be written like this. So you can, and it is clear that if you take eta is equal to 0, you have this equation is equal to this. So you have a continuum, okay? Either you use some information or not. So it is just this. So I take for simplification just one decoherence process associated to the jump operator L, okay? So I have this equation, so with the Wiener things, and if you use the Ito rules, you can write down this differential equation this way, where here you have your measurement operator depends on the measurement outcome. And it is given by, it is something which is close to identity, plus something, and here you have the injection of the knowledge of your system. And if you normalize with the trace, you obtain exactly this. Just use Ito rules of computation. So, and this could be quite useful for simulation, for example. If you want to have a numerical scheme that preserves the positiveness of rho, it's nice to use this, because you know that rho will be always positive. Here, if you use a standard numerical scheme, you may be some small negative part on rho, especially when rho is close to a pure state. You are close to the edge of your domain. So here it will be, it's a nice way to do some simulation, preserving trace and positiveness of rho. Okay. So you can do exactly the same thing for Poisson process. Okay, for Poisson process, you had some imperfection, so which means that here it is corresponding to short noise. You have always something, which is not. And here you have something which is related to detection efficiency. Okay, so you have two numbers, the short noise and detection efficiency between 0 and 1. And in this case, the dynamic equation is this one, taking into account short noise and detection efficiency. Okay? And if you detect something, then you know that the collapse is something like this. And if you detect nothing, then you say 0 and you take this thing. And you obtain exactly the same structure. So partial cross map and you normalize. Okay? And this normalization also gives you some, is connected to the probability of detecting these things. Okay. So you can mix both. If you have Wiener process and Poisson process, exactly this. So if you have a detection, it doesn't change. But if you have no detection of jump, then you have still your continuous detection. Then you have changed a little bit your operator here by adding this. Okay, and you obtain exactly the same thing. So you can continue. So now I think that you can do a lot of things by combining all these things. Okay, and this can be used for numerical integration. I think this kind of thing. Okay. And now maybe to mimic what is going on for filtering. So filtering is this issue. So you know that your system is given by this. And you know that your outcome is this. So just replace dW with respect to what you know, which means dW, it is dy minus this thing. So just put in this equation, replace dW by dy minus this point. You obtain exactly this equation and replace rho by rho estimate. It is exactly what we have done for quantum filtering in the discrete case. So this is the quantum filter, okay, associated to this measurement here. Just replace this by the difference between the variation of y and, in fact, I would say the deterministic part of y. So the information is given by the slope of your signal. Okay? Not by the fluctuation. So it is clear. And here so now what you have, if you want to consider stability of quantum filtering, you have a quantum chain, quantum process which has two states, rho and rho estimate. They are driven exactly by the same Wiener process, so okay, dW. But here you have something which is different when rho is different to rho estimate. So it is very similar to a prediction, which means that you copy this thing, okay? And then you correct this thing when, in fact, your estimate, in fact, is different. So it's something which is quite, and you can do this just by knowing why, your measurement. So you have prediction correction. So something which is what we call in classical system theory an observer. You copy your system, and then you take some correction term when the state estimate is different to the state of your system. So you change a little bit the equation. And in this case, what you can prove, it is almost, we have done this in a much more mathematical setup with Addis and Clément Pellegrini, a colleague from University of Toulouse, is that the fidelity is always a sub-martingale for this system. Okay. Now, I think I will conclude now by one question. So it is about this problem of stability of the quantum filtering. But what we have, it seems, that we have is that 1 minus the fidelity is always a super-martingale, which is a kind of contraction. So you know, as Michael said, is that Krauss map are contraction. Okay? But in this case, you are in the deterministic case. And Krauss map are contraction for a lot of metrics. Okay? And you have, in quantum information, you have a nice result by Dennett Spetz, where he has, in fact, characterized all metrics that are contraction for Krauss map. And in particular, the metric coming from the fidelity is a contraction, the biometric, okay, in this case. But I have checked that other metrics that are contraction for the Krauss map are not contraction for filters. So if you want to find a way to measure the distance between rho and estimate, you can use the fidelity. It is a good metric. But maybe you have other metrics that works for any quantum filters. But I don't know if the fidelity is the only one or not. It is clear that if you want to find such metric, you have to take it in the metrics where characterized by the work of Spetz, okay? That are contraction for, in fact, any Krauss map. So above all the metrics that are contraction for any Krauss map, you know that the metrics from the fidelity gives you a kind of contraction, I would say, average, okay, for quantum filters, but maybe you can have other one. For example, the relative entropy is not a contraction. So a super-martingale for quantum filters, you can prove that. But it is something which is a contraction for Krauss map, something like this. So you have a difference. Okay, thank you.
Could you go back to a couple of slides to the next one? Next one.
Mm-hmm.
That one. Okay. Your discrete time Markov model there. Have you compared that to the sort of standard Milstein method? And what?
Milstein method to increase the. Yes, you can. A Milstein scheme, numerical scheme to integrate, where you have something, because with this numerical scheme, you have an order of a square root of dt. Okay? And the Milstein scheme, your order of truncation is dt. Okay? If you take an Euler scheme.
there's a correction which is.
And here, if you want to do this, you have to add a correction here, which is more or less something which involves the L square. And if you want to convert this to a Milstein scheme, numerical scheme,
I'm not saying you should convert it to a Milstein, but the Milstein scheme uses the next highest or higher order terms, the standard Euler
Yes,
method.
yes.
So have you compared this to the Milstein in terms of accuracy and stability? I tend to use the Milstein pattern method for numerical integration. So I'm interested in
But
this.
there is a Milstein formulation of this. So you can this corresponds to the Euler scheme.
If I took the equation at the top, the increment,
Yes.
and I integrate that using the Milstein scheme,
Yes.
okay, is your method better than that? More accurate?
So
The Milstein scheme is strongly convergent to first order, which the Euler scheme isn't.
So if you had something here, okay, another operator of the same form, but with something else, okay? Here, you have something here. You obtain, when you use Ito computation, okay, when you use a scheme here, a Milstein scheme here. So we can formalize this scheme as this one. So this scheme of integration, okay, can be written like this one. And what you gain is that you preserve automatically the positiveness of both, which is not true in the Milstein scheme.
Okay, yeah, I mean, the Milstein scheme, one of the problems, or I think it's the numerical integrations of the top equation, is you get purities greater than 1, I think is what you.
Yes.
So your scheme guarantees that
Yes.
you don't. Okay. What happens if something like the Hamiltonian is mismatched?
The Hamiltonian mismatch, what do you mean?
So the Hamiltonian is not quite correct.
Which means that if you change H.
No, but the point is that you generate, your estimate is based on an assumption or some estimate of what the Hamiltonian is.
Yes.
If the Hamiltonian is not correct.
So you have to define what is the correct Hamiltonian. If you have a
parameter
uncertainty.
Yeah.
You have a parameter uncertainty.
Is your scheme stable under that error?
Numerical scheme?
Yeah.
I don't know. So I have not checked this. But I know that the Milstein scheme can be formalized this way. I have used it.
I mean, I would be interested in trying your scheme to see if it's better than the scheme.
Yes.
But if the Hamiltonian is uncertain, maybe you can put that as a parameter and filter it as well.
Yes.
You can. I've done some work with Kurt Jacobs on that as well. I know people have worked on it,
but yes.
Essentially, the way I look at it is that the state of the system, the density matrix, the conditional density matrix, represents your state of knowledge of the system. Something else is producing. I mean, one of the other comments that you made, I think in the previous slide, where you said that the two, maybe it's a bit later, that the two things were driven by the same increment, by the same GW.
Yes, this one.
Yeah. I mean, the top one is, if you like, the state you have no access to. Is that right? Only numerically.
The top one is the state where you have a good initialization. And this one is the state where you have a bad initialization. For example, you initialize this to identity, and here you know that your system is not in the identity state, but you don't know what it is. And the main issue is what you want to learn through the measurements, through the evolution of the system, what is the state of the system. But not initially, but after a certain time of measurements where, in fact, you collect some information. If you have no information on your system, so I will say if you take a pure physicist point of view, I say, well, you take these things, okay? It is not these things. If you have no information of a system, if you want to to compute, in fact, the state of the system, you use your measurement and you use this recurrence. And this gives you the good information of the system. And the fact that this system is stable in the sense that rho tends to rho s tells you that this filtering process is something which is stable. It tends to forget its initial condition. So if you have some small error and so on, even in your numerical scheme, it might be not a problem. Okay? It is clear that if you take an unstable, exponentially unstable system and you take a numerical integration of it, after a certain time, okay, it diverges, whatever scheme you have. Okay, and here it's seen that this is a filtering, a filter, which means at least a stable dynamical system. Just this. Okay.
Just to remark that in the classical filtering theory, there are methods to ensure that, say, the probability density remains positive and normalized to 1. I think Hal Kushner, had some of the early ideas on that back in the 70s, I think.
Oh, maybe.
And Francois Leblond, who you may know at INRIA, is expert on such things.
Wait, is?
Francois Leblond.
Ah, yes. Okay, so I will contact
You
you.
should contact him, he'll be expert on these things.
On this.
Jake? Oh, well, it's largely been addressed because I too am concerned about parameter uncertainty. But the other half of that, so that I feel like we've talked about enough, but let me ask the other part of the question, which is, in many sort of practical settings, because you're limited in your set of measurement abilities, it seems to me that one might prefer to work in the Heisberg picture and update your model of operator potential measurements rather than work in the Schrodinger picture with the density matrix. And in particular, this experiment's beautiful, right? And the theory is beautiful, but if I wanted to reproduce this with superconducting circuits,
Yes.
that's too fast.
That's too fast, yes, clearly.
So
You do not have
one
time
needs
to...
some reduction of the computational part of the problem.
You do not have time to integrate this, clearly.
So any advice?
Coherent feedback. Or maybe Markovian feedback. Markovian feedback with circuit could be the idea of Wilborn and Bisman. It's quite nice because in closed loop you have still you can change. For a Markovian feedback, what you can change this operator by static feedback, output feedback. So you change this operator, you have a shift on H2, and it could be quite nice. So I'm looking a little bit this with Benjamin Huard and at École Normale, who is working on the quantum circuit, this kind of feedback, because we do not have time to do the computation. It seems to me that the Serge Haros experiment is the only experiment where you have time to do the computation in the world. Maybe I'm wrong, but...
It seems important that the hardware